Imagine stepping into a taxi, giving the driver your destination, and then, just sitting there while the meter starts running.
Right.
But the taxi isn't moving. Instead, the driver pulls out a toolbox and spends the next, 10 minutes physically building the engine right there in the driveway.
It sounds totally absurd, but honestly, if you run heavy data workflows in the cloud, you are probably paying thousands of dollars a year doing exactly that. Just sitting there, watching your computing clusters figure out how to start up.
Right. And that meter is splitting the entire time. Every single second that a cluster just sits there in the cloud, provisioning itself, downloading packages, and organizing its dependencies, you are burning through your compute budget.
Oh, absolutely, without actually processing a single row of data.
Exactly. Which brings us perfectly to our mission today. Welcome to this deep dive where we are unpacking a highly specific but highly impactful technical document.
Yeah, the Syntasa 9.0.1 release notes.
Right. So we are looking at this stack of documentation that focuses, well, almost entirely on bug fixes and major enhancements for Spark on Kubernetes, or K8's workloads, as they're often abbreviated.
And as we comb through these notes, one massive overarching theme became incredibly clear to me.
Friction reduction.
Yes. It is just a relentless attack on waiting. I mean, this 9.0.1 update targets the core bottlenecks of data science workflows. Specifically, we're talking about dependency management, initialization scripts, and runtime efficiency.
It really applies these fixes across the board, right? Like whether you are running massive scheduled batch jobs or if you're actively coding in an interactive notebook.
Right, exactly.
Okay, let's unpack this because solving that taximeter problem really starts at the very beginning of the pipeline. Before you can execute a complex data model, your Kubernetes environment actually has to boot up.
Which can be painfully slow.
Yeah. And the release notes point out a major shift here regarding how the system handles Python. They've introduced what they call pre-baked Python environments. But, before we talk about the fix, help us understand why the old way was so slow. Why was this system basically building an engine in the driveway?
So to really understand that delay, we have to look at what a Conda environment actually is. Because, Conda isn't just a simple download manager.
Right. It's a lot more involved.
It really is. When you tell a cluster and need specific Python libraries to run a job, Conda acts like this highly complex puzzle solver. It has to look at every single package you requested, check the versions, and resolve the entire dependency tree.
Just to make sure none of the packages conflict with each other.
Exactly. And this is a computationally heavy process. In previous versions, every time you spun up a Spark on Kubernetes batch job, the system had to do this puzzle solving from scratch at runtime.
And the notes state this created a mandatory 2 to 3 minute delay, like just a built-in waiting period before your code even thought about executing.
Yeah, that's the engine building right there. But now, Syntasa has shifted to utilizing pre-installed Python environments.
Okay.
They are specifically including versions 3.7, 3.9, 3.0, and 3.11 right out of the gate natively within the image.
Okay, so mechanically speaking, how does that actually change the boot sequence?
Well, it completely bypasses the puzzle-solving phase.
Oh, nice.
Because the environment is pre-baked into the system image, the correct Python version activates instantaneously based on your job configuration. The system simply, points the runtime to the existing pre-resolved environment.
So the environment
It's just there, ready to go.
It's like checking into a hotel, and the room is already fully furnished. You don't have to assemble the bed from IKEA parts before you can go to sleep.
That's a great way to put it.
But I do have to play devil's advocate here for a second. If I'm running a massive batch job that takes, let's say, 4 hours to complete, is shaving 2 or 3 minutes off the startup time really that revolutionary?
What's fascinating here is the cumulative effect, both on the infrastructure side and human psychology. Let's look at the compute side first.
Okay.
A data engineer isn't just running one 4-hour job a week. A standard pipeline might involve dozens, if not hundreds, of smaller validation jobs, tests, and transformations every single day.
Oh, wow. Yeah, I see where you're going with this.
Right. If you lose 3 minutes on every single startup and you have 50 jobs running, that is 2.5 hours of wasted compute time.
Hours where you were just paying Amazon or Google or Microsoft to solve a puzzle it already solved yesterday.
Precisely. And beyond the hard cost, you have to consider the cognitive friction. 3 minutes is, frankly, a really dangerous amount of time for a developer.
How do you mean?
Well, it's just long enough for you to switch tabs, check your email, get pulled into a Slack thread, and just completely lose your flow state.
Oh, yeah. You switch context, and then you forget what you were even doing.
Exactly. Instant activation preserves the developer's concentration.
That cognitive cost is huge. Okay, so we've solved the problem of the environment taking forever to wake up. But, waking up fast doesn't mean the cluster actually knows what to do for your specific project.
Right, it still needs its tools.
Exactly.
Yeah.
So how does a cluster learn what custom scripts or libraries it needs without, slowing down the whole process again?
Well, that leads us into what I consider the most architecturally interesting part of 9.0.1, and that's the unified dependency and init script management.
Sounds heavy.
A bit, yeah. Syntasa has basically built full Kubernetes support for initialization scripts and dependency configurations across both driver and executor pods.
Okay, let's define some of that architecture for anyone who might not live and breathe Kubernetes every single day. When we say driver and executive pods, what exactly are we visualizing here?
Sure, think of a Spark cluster like a massive construction site. The driver pod is the foreman. It holds the blueprint, manages the schedule, and tells everyone what to do. The executor pods are the worker bees. They're the ones actually pouring the concrete and swinging the hammers.
Right.
For a construction site to function properly, both the foreman and the workers need the same safety briefings and the right tools.
And those tools are the initialization scripts, pip packages, and JAR files.
You got it.
The release notes highlight that K8's executors now run global, notebook, and runtime init scripts during their bootstrap phase. So every worker bee wakes up and receives the exact same instructions before they even start the job.
It guarantees uniformity. And Syntasa really streamlined how you deliver those instructions. They've added new Spark properties, specifically the property syntasa.python and syntasa.jar.
Okay, so if you need a specific Java archives, like a JAR file, you just provide its Maven coordinates,
The bot on.
which is essentially just the exact address the system uses to locate a specific piece of code in a massive public library, right?
Yes, exactly. You provide that coordinate, and the system automates the rest. It pulls the JARs directly into the CSpark home jars directory, and it handles the pip installations across the cluster automatically.
Wow, so it abstracts away a massive amount of manual infrastructure routing.
It really does.
And the visibility into this process got a huge upgrade too. The output of these global and runtime init scripts is now streamed straight to the Syntasa UI log viewer.
Which is fantastic.
Yeah, so if you configure a script at the platform level, you don't have to go spelunking through raw Kubernetes pod logs in a terminal just to see if it executed correctly.
Oh, it saves an enormous amount of troubleshooting time. No one wants to dig through raw terminal logs.
Speaking of troubleshooting, there's a detail in this section labeled resilience that genuinely confused me at first glance.
No. Which one?
The notes say that init script failures are now non-fatal.
Ah, yeah.
So if an initialization script exits with an error, the job will just launch anyway and log a warning. Why on earth would we want a job to continue if its setup fails? Like, going back to your analogy, if I'm missing a tool, shouldn't the whole construction site shut down before it builds something wrong?
I get why that seems counterintuitive. That actually touches on a classic debate in software engineering, fail fast versus fail safe.
Okay.
If we connect this to the bigger picture of fault tolerance in massive distributed systems, the logic becomes pretty clear. Imagine your init script is pulling in, say, 20 different auxiliary packages.
Right.
19 of them install perfectly. They are the core machine learning libraries you absolutely need to process the data. But one package, maybe just a minor formatting library you use for a secondary visual output, fails to download.
Just because of a glitch.
Yeah, like a temporary network blip on a third-party server.
Ah, I see where this is going.
Right. Under the old fatal rules, that single network blip would trigger a hard stop. It would instantly nuke a massive, multi-hour data processing job before it even started.
That would be so frustrating.
It is. You would come back to your desk the next morning expecting processed data and instead find a dead job over a formatting package you might not have even needed for that specific run.
Oh, man. So by making these failures non-fatal, Syntasa puts the power of context back in your hands.
Exactly. It trusts you, the user, to understand your own pipeline. You can check the logs, see the warning, and decide for yourself if that missing formatting package is a deal breaker or if you can just proceed with the core data.
And they made checking those logs a lot more effective, didn't they?
They really did. They fixed a bug where JAR files specified in runtime configs weren't installing correctly on K8s, but more importantly, they overhauled the error messaging itself.
Right, replacing the generic compilation failed messages.
Yes, instead of a useless compilation failed, the system will now explicitly tell you it through a class not found exception
Yeah,
in both short and detailed log views.
it goes from a frustrating guessing game to a targeted, actionable debugging task. Okay, so up until now, we've really been talking about background setups, right? The heavy automated batch processes running in the dark.
Yeah, the invisible stuff.
Here's where it gets really interesting. Let's bring this into the light, to the interface you actually interact with, everyday interactive notebooks.
Oh, notebooks. They are the central hub for a data scientist. It's where the active experimentation happens. And historically, the biggest source of friction there has been the infrastructure overhead of simply spinning up the workspace.
Which brings us to the concept of runtime reuse. And I mean, this is arguably the most impactful daily feature we're looking at today.
I would agree with that.
Notebook process jobs and notebook cards can now actively reuse existing running Spark on Kubernetes runtimes. Previously, these jobs would just stubbornly trigger the creation of a brand new cluster every single time.
Yeah, and now in the notebook runtime settings, there is a Select an Instance drop-down menu. It actively displays all the running instances that share the exact same template. You can just select an environment that is already warm and ready.
My mind instantly goes to, like, a factory conveyor belt.
Oh.
Yeah, instead of building a brand new, highly specialized robotic arm every time a new product comes down the line, which takes forever and costs a fortune,
Yeah.
you just route the product to a robotic arm that is already powered on, calibrated, and perfectly capable of doing the work.
That is a much more accurate way to look at it than just sharing a taxi ride. And Syntasa actually optimized the underlying mechanism of how the system catches these environments.
Right, they fixed the logic around a setting called terminate on complete equals false.
Yes.
How does that actually work under the hood?
So when a job finishes on a Kubernetes cluster, the cluster doesn't just vanish instantly. It enters a scale down or a tear down phase. It's shutting off processes, releasing memory, basically preparing to terminate.
Okay, making sense.
Previously, once it entered that phase, it was basically dead to the system. You couldn't use it. But now, the logic can successfully intercept an idle cluster that is right in the middle of scaling down.
Oh, wow.
It reverses the teardown and instantly reuses it for your new jobs.
That is brilliant. It's like catching an airplane at the gate right before it pushes back.
Yeah.
The crew is already there. The engines are warm. You just walk down the jet bridge and board the new passengers. You don't have to schedule a whole new flight.
And the cost savings there are profound. I mean, cloud providers bill you for the lifespan of these clusters. Constantly creating and destroying redundant clusters is incredibly inefficient.
Not to mention expensive.
Exactly. Reusing a warm runtime slashes your cloud spend, which makes the finance team happy. And simultaneously, it keeps the data scientist in a state of flow, which makes the engineering team happy.
Win-win. And speaking of keeping the team happy, let's talk about Scala kernel parity. Because sometimes it feels like Python gets all the shiny new toys in data science, while Scala, which Spark is actually written in, gets treated like a bit of an afterthought.
Yeah, but that parity is vital for cross-functional teams.
Yeah.
Data scientists often prefer Python, right? But heavy-duty data engineers frequently rely on Scala for deep Spark optimizations.
Right.
In 9.0.1, the Scala notebook kernel now shares the exact same robust initialization logic as the Python kernel. It fully supports those runtime scripts, the dependency configurations, and the automatic class path inclusion for JAR files we talked about earlier.
So no matter what language you're writing in, you get the exact same streamlined infrastructure support.
Yes, exactly.
But the feature that really highlights how deep this friction reduction goes is the optimization around ad hoc package installation. We're talking about the commands sentinels.install PyPI and sentinels.install conda package.
Oh, this is a masterclass in removing computational overhead.
How so?
Previously, if you were working in a notebook and realized, oh, I need a new package halfway through, running those ad hoc commands would trigger an operation called condapack.
And from my understanding, condapack is an absolute beast.
It is a massive I/O bottleneck. Condapack literally takes your entire functioning conda environment, archives it into a huge tarball file, ships that massive file across the network to every single executor pod, and then unzips it.
That sounds horribly inefficient.
It's the equivalent of packing up your entire house into moving boxes just to bring a new chair into the living room.
Oh my gosh, that's absurd. And the release notes say this bundling process was adding anywhere from 30 to 90 seconds of dead wait time just to install one ad hoc package.
But optimized for Kubernetes in 9.0.1, the system skips Conda entirely.
Thank goodness.
Right. Instead of bundling the house, Kubernetes tracks the specific ad hoc package you requested and dynamically instructs the executor pods to simply pull and install that specific package locally during their own bootstrap phase.
It just delivers the chair. That is such an elegant mechanical solution. It achieves the exact same goal, but it trims away 90 seconds of heavy lifting. But, as we know, shiny new mechanics don't really matter if the foundational chassis of the platform is cracked.
It's very true.
You can have a lightning-fast system, but if it fundamentally breaks your code, it's useless. Which brings us to the final portion of the release notes, the invisible fixes, the vital under-the-hood stability and bug fixes.
And these are the exact types of bugs that completely erode a developer's trust in a platform when they occur.
Oh, for sure. And the first one listed is the custom script formatting bug. I have to admit, reading this triggered some secondhand anxiety for me.
I don't blame you.
Syntasa resolved a highly frustrating issue where custom runtime scripts were literally losing their indentation and their line endings when they were saved to Amazon S3.
Which is catastrophic for a bash script.
I mean, why is that so catastrophic? Why does a line ending matter so much to the machine?
Well, it comes down to how different operating systems read invisible text characters. Windows uses a combination of characters called carriage return and line feed to end a sentence. Unix and Linux systems just use a line feed. S3, or sometimes the text editor itself, was stripping or converting these invisible characters.
So when the Linux container in Kubernetes tried to read the script,
It encountered a hidden Windows character it didn't understand.
so it crashes.
Violently, it usually throws a totally cryptic command not found or syntax error.
Oh, that is just the worst. Which means you are sitting there staring at a perfectly written script, pulling your hair out, trying to find a syntax error that doesn't actually exist
Right.
because the system mangled your file behind the scenes.
Yeah, it's maddening.
Resolving that is a massive sanity saver.
Yeah.
They also squashed an instance visibility bug in the UI, right?
Yes. This was an issue in the notebook cards where a newly created runtime instance was totally invisible in the drop-down menu until it reached a full running state.
So even if the cluster was successfully initializing, it was just a ghost. You couldn't select it, you couldn't monitor it.
Right. It felt like the system was actively hiding your own compute resources from you. Now, they populate immediately, so you actually have situational awareness.
And finally, they addressed a Conda override failure specific to AWS environments.
Right.
If a user set the property syntasa.override.conda.env to true, it inexplicably caused errors with Boto 3.
Yeah.
And Boto 3 is the official Amazon Web Services SDK for Python, right?
Right.
It's how your code actually talks to AWS services like S3 or EC2.
Which means if Boto 3 breaks, your environment essentially goes blind and deaf. It completely loses its ability to interact with the surrounding cloud infrastructure.
Yikes.
Yeah. By fixing this, Syntasa ensures that custom Conda environment overrides play perfectly nicely with the underlying Amazon architecture.
So let's step back and look at the whole picture here. We've explored pre-baked environments, skipping the dependency puzzle, init scripts failing safely, the brilliance of intercepting teardowns to reuse runtimes, and squashing those invisible bugs.
Right.
What is the ultimate takeaway for you, the listener, trying to build better workflows today?
I think the biggest takeaway is that this platform is actively trying to get out of your way. Syntasa 9.0.1 is fundamentally an anti-friction release.
Yeah, that makes sense.
Knowing how to leverage these specific tools, like actively choosing to reuse a warm runtime from the dropdown, or utilizing the optimized Syntils commands to bypass heavy archiving, it allows you to immediately make your Kubernetes workloads cheaper and faster.
You are reclaiming hours of compute time.
Hours! And preserving your own cognitive focus.
The system is handling all the heavy lifting of the infrastructure, so you can actually just, do the data science.
Exactly. But looking at all this automation, this raises an important question for us to ponder. As these platforms get increasingly intelligent at predicting and handling our environment needs, like pre-baking dependencies, invisibly intercepting idle clusters, or routing packages without our input, are we moving toward a future where the entire concept of infrastructure setup becomes completely invisible to the data scientist?
It certainly feels like the scaffolding is disappearing, doesn't it?
If the platform just handles all the routing, all the fault tolerance, and all the cost-saving scaling automatically behind a curtain, what happens to our foundational understanding of the systems we build on?
That's a great point.
If everything just magically works, do we eventually lose our engineering edge, or are we finally truly free to focus purely on the data?
That is a phenomenal, provocative thought to leave on. We started this deep dive talking about the expectation of instant magic in cloud computing.
Hmm.
The desire to just flip a switch without the muddy reality of waiting.
And waiting is expensive.
Very. With updates like Syntasa 9.0.1, the wait times are vanishing, the friction is fading, and that magic is becoming an operational reality. Thank you so much for joining us on this deep dive. Until next time, keep optimizing and keep questioning how magic actually works.